Hi everyone, I'm Tosif Ali and I'm a graduate student at Arizona State University working under the supervision of Professor Chris Richmond. In this presentation, I will talk about the detection bounds for the cognitive radar framework. Particularly, this work will try to answer a very basic question that what is the optimal receiver architecture when the clutter and target channels are modeled as random matrices. This is the outline of my presentation. First, I will introduce cognitive radar and talk about the typical data model adopted in cognitive radar framework. So in a conventional radar, the transmitter transmits a fixed waveform from the for the whole duration of the mission, and there is no feedback from the receiver chain to the transmitter. On the other hand, cognitive radar systems are proposed that adapt the waveform throughout the mission. The main ingredients of cognitive radar includes feedback from the receiver to the transmitter, a database of information, and adaptive signal processing chain. The radar environment is typically modeled as responses from a clutter channel as well as target channel plus waveform independent noise. Classically speaking, radar data is often modeled as complex Gaussian. The mean of the distribution represents the signal or target part of the observation. Here, alpha represents complex target reflectivity and is a function of the transmitted waveform S of t. And V is the space-time staring vector, which is a function of the target azimuth, elevation, and Doppler. While all the stochastic part of the observation like noise, jamming, and interference and clutter are characterized by the covariance of the distribution. The covariance matrix is modeled as sum of covariance matrices of system noise, jamming or interference, and clutter. It is reminded that the clutter itself is a function of the transmitted waveform, and hence using the classical model to optimize the waveform becomes a non-convex problem. To address this issue, channel matrices-based approach is adopted in which the clutter and target responses are modeled as the output of LTI systems, which is the approach usually applied in communication systems. Hence, the response from a target can be represented as transmitted waveform S of t multiplied by the channel matrix H sub t. Similarly, the response from the clutter can be represented as transmitted waveform multiplied by the clutter channel matrix H sub c, and hence the clutter response is also dependent on the same waveform which illuminate the target. Finally, in the general MIMO model, the received data consists of contributions from signal-dependent responses from clutter and target channels and signal-independent noise. Generally speaking, the channel models for the target and clutter will be different. Notice that this model is linear and hence it simplifies the waveform optimization problem. These matrices are usually modeled as random matrices. So even though this is a very simple linear model, we are asking a very basic question in this work that if we model the channel matrices as random, what is the optimal detector for cognitive radar framework based on general MIMO model? Is it just a linear filter? So to answer these questions, next I will talk about the derivation of target detection bounds. First, when the channels are modeled as known and deterministic and using the likelihood ratio test, and then modeling the channels as unknown and stochastic and using the average likelihood ratio test. So consider the channel matrices H sub c and H sub t as known and deterministic, then the distributions under H naught, that is when the target is absent, and under H1, that is when the target is present, or complex Gaussian as shown over here. The resulting test statistic under Neiman-Pearson criteria is coherent match filter and is given by T tilde, shown over here. This is a very well-known result and it's been around for a very long time. Our goal here is just to show you its performance for this particular choice of model. The raw performance given in terms of complementary error function, IRFC, is given by the last equation on this slide. Notice that the raw performance is driven by what we recognize as the integrated signal to interference plus noise ratio. Next, we consider the case when the channel matrices are modeled as stochastic. So when a radar illuminates a target, the reflected signal reaches the receiver via the direct path as well as via multipath. So using the Riccian model, each channel matrix can be decomposed into direct or deterministic component and uh, diffuse or stochastic component. Here kappa is the Riccian factor, and this factor controls which component dominates. The deterministic component represents direct path bright scatterers, while the random stochastic component models the diffuse scatterers due to multipath. So here is our received data model again. And the noise considered here is a waveform independent complex Gaussian. Channel matrices are assumed jointly Riccian, which is the standard model for explaining scattering phenomena. This means that our channel matrices are complex normal with some known mean HT bar and HC bar, and covariance matrix sigma sub h. To find the covariance matrix, I am simply stacking the columns of the matrices H sub t and H sub c and forming a long vector, and then finding the covariance of that vector. The sigma sub t component of this covariance matrix captures the covariance of columns of the target channel or matrix. Sigma sub c captures the covariance of the columns of the clutter matrix. And sigma sub ct and sigma sub tc captures the cross correlation between the columns of the two channel matrices. So the problem under consideration requires composite hypothesis testing. We are using average likelihood ratio test, which will simplify this problem to that of a binary hypothesis testing problem by simply integrating over the PDFs of channel matrices. Since the channel matrices and noise are considered as Gaussian, the properties of Gaussians simplify this integration, and we get data observation under hypothesis, which is once again Gaussian. And all we have to do is to find the mean and covariance of the data under each hypothesis, which is shown over here. Here, R sub Cn is the contribution to the covariance due to the system noise and clutter component. And notice that it depends on the waveform. R sub Ct is the contribution to the covariance due to the presence of target. Notice that the covariance part of the target depends on the not only on the sigma sub t, but also on the cross correlation of the target and clutter channel matrices. The expressions for these sigmas were shown on the previous slide. So the ALRT yields maximum average probability of detection for any fixed average probability of false alarm, where average is over channel matrices. Next, we take the distribution under each hypothesis shown on that were shown on the previous slide, and using the expression for the ALRT based test statistic. Here we define X naught as the data observation minus what we know best about the clutter. The final form of the LRT based test statistic consists of two parts: a coherent match filter and a pre-Whiten energy detector. It is interesting that the ALRT tells us to add these two different detectors together. The expressions for the vector W and matrix A are shown over here. Notice that in each case, whether coherent match filter or a pre-Whiten energy detector, the first thing that the data vector C is the inverse of the clutter and noise covariance matrix R sub Cn, and that's where the pre-whitening aspect come into action. So the first component of the ALRT receiver is similar to T tilde sub LRT, but based on the mean channel matrices HT bar and HC bar. It simply says to subtract from the observation what we know about the clutter and then apply a coherent match filter towards left. This part actually exploits the bright scatterers. The pre-Whiten energy detector part caters for the stochastic part of the target by subtracting from the data observation what we know best about the clutter as well as the target, and then projecting on the subspace that defines the stochastic part of the target variations. and hence with the pre-whitening energy detector, ALRT performance is enhanced. Next, I will discuss numerical results. So here we are considering a very simple example just to see the effect of pre-whitening energy detector and when its benefit starts to kick in. So consider a radar system consisting of a uniform linear array of 5 elements, illuminating an environment consisting of a point target with 0 Doppler at 30 degrees with respect to the array broadside, and 2-point cluttered sources, one at 1 degrees and one at 0 degree with respect to the array broadside. Both point clutters are considered as assumed as stationary. The noise is considered here as complex Gaussian with zero mean and variance of 0.1. The transmitted waveform is modeled as S equal to alpha times S hat, where S hat is a fixed waveform and alpha is just to vary SNR in order to plot the ROC curves. H sub T and H sub C, which are the channel matrices for target and clutter, are assumed uncorrelated with covariance matrix given by sigma equal to sigma sub H square times identity matrix. This slide shows the ROC performance results of a very special case in which we perfectly know the channel matrices. I'm plotting the probability of detection versus SNR for 3 different choices of probability of false alarm. So in this case, as soon as the signal level exceeds the noise, we see the detection performance go up. This is the case when my channel matrices are random with variance of 0.1. Again, H sub CT and H sub C are assumed uncorrelated. We are comparing ALRT with LRT based on the mean of the channel distribution, which is also the first part of ALRT. The solid curves is for the ALRT and the dotted is for the LRT. These curves are plotted for 3 different choices of probability of false alarms. As you can see, the detection performance of ALRT is slightly better than LRT. As I increase the variance of the channel matrices from 0.1 to 0.2, then 0.3, and 0.4, and so on, the second part of the LRT, that is the energy detector, becomes more and more significant in terms of the detection performance. It's interesting that most of the gain is coming from the match filter. And we know this because the dashed curves are very close to the solid curves. There is improvement in ALRT over LRT due to the energy detector part. And this improvement is very small when the channel matrices are less random. But as we increase the variance of the channel matrices and make the channels more random, there is more improvement in ALRT over LRT. But there is also degradation in the overall achievable performance. So these are just our initial observations, and we will be exploring some more scenarios as we continue to dig into this problem. Next, I will summarize our findings. In this work, ALRT-based receiver architecture for Ricean channel models based cognitive radar is derived. And ALRT-based receiver came out to be consisting of 2 parts. One is coherent match filter, and the other is pre-whitening energy detector. We also found out the answer to our question that the optimal statistic when the channel matrices are random is not strictly a linear filter. And finally, ALRT provides insight for structure of optimal receiver architecture. Thanks for your attention. Please let us know if you have any questions.